want, but we keep in mind that u is going to be the thing that we're going to take the derivative of, and dv is the part that we're going to take the integral of. So if we are clever in how we choose those parts and plug into our formula, hopefully we get something that is easier to work with, and therefore we can break down our integral. So before we kind of work with the concrete example, let's go ahead and look at this formula in case you're a visual learner, so I can show you what the actual equation looks like. So here's my whiteboard, and let's write out the key formula to know. But I figured I'd just give you that kind of first little explanation before we look at the formula, because it can be kind of confusing. So the integral of u dv equals uv minus the integral of v du. This is the key formula to memorize. The integral of u dv equals uv minus the integral of v du. So notice here we have those four parts that I mentioned before. So if we have an integral, then we want one part to be u, the other part to be dv, so that we take the derivative of this, and notice that du is here, and the dv will give us v, so we just plug in this u, this v that we take the integral of, minus the integral of that v that we calculate, and then we have du. So basically for this integral, we swap these. Instead of u dv, we have v du. So notice that this formula doesn't actually give us an answer, it just gives us something equivalent. But like we said, if we are clever in how we pick v and du here, in this technique, this integral should be easier to work with, so it should give us a step closer to the actual integral. Sometimes you can just go ahead and use another one of our techniques to calculate this integral, and it just works out and you can do it in 2 steps. Sometimes you need to do integration by parts again to break this integral down further, and still sometimes you can, well, it depends on the actual function itself, but sometimes you end up or sounds rather. I don't think I've ever seen this before. Talk about ultra, ultra, ultra rare. I kind of incorporate some throughout my videos, but here's a first one. So, let's get this formula memorized, okay? The integral of u dv equals uv minus the integral of v du. This is gonna be the weirdest, nerdiest thing I've ever done. The integral of u dv equals uv minus the integral of v du. The integral of u dv equals uv minus the integral of v du. I'm just wondering to speak. And that is because this isn't a property of the integral, which is really founded in the idea of a Riemann sum. Remember, so the integral is actually all about summations. So we can't just multiply like this without distributing some stuff. So we cannot just do x squared over 2 times whatever this is, 1/2 e to the 2x. So no go for basic integrals. This is not a u substitution case because it kind of looks like it could be, but the only thing that kind of makes sense to simplify with the u sub would be 2x. And so we would have e to the u, but the derivative of 2x is 2, and we have a factor of x here to deal with. So we cannot completely convert this into a function of u and du only without still having an x. So no u substitution here. If the question were x e to the x squared, though, we could, because the derivative of x squared is 2x, and so we could have this factor of x here and then have a constant, which is no problem. But because we have 2x here and an x in front, this is not a u substitution case. This is not going to be trig substitution because there's not much here to work with. If we were to let x equal something else like sine u or something, that just makes it more complicated, and there are no identities here to simplify, so none of those. But when we have integration by parts, what's nice about this is I have this polynomial. It's a very simple one, it's just x, so a monomial, but if I think about the derivative of x, I get 1. So this is kind of a nice candidate for u because du would be just dx. So when I use the integration by parts formula, that part just goes away. And then we would check if this is okay to integrate because the rest would have to be dv, and that's decent to do. So I think that's what I'm going to go ahead and do here. So polynomials in front are usually really good candidates for this because as you take derivatives of polynomials, the degree, which is the highest exponent power, gets reduced by 1 every time. So it kind of just simplifies our function each time we do this. So here's our formula again. And in this case, I'm going to let this be u and this be dv. So you definitely want to write this all out. So let u equal x and dv equal e to the 2x dx. It doesn't always work out exactly like this. Sometimes you'll have like e to the 2x is u and x dx is dv, so it's not always, from left to right. That's up to you to choose. So the whole goal is to make this part simpler, especially this integral part simpler to calculate. It's not wrong to pick ones that are complicated. The equation still holds, but if you just get something just as complicated in this integral, then there's kind of no point in using this technique. So it's not like you can really go wrong in picking u and dv, but if you want to get anything helpful out of this formula, you kind of want to pick something that simplifies your work. So I picked u and I picked dv. Let's calculate the remaining parts in our formula here. So from u equals x, I calculate the derivative, which is 1, but then we have dx. Because we're taking the derivative of x with respect to x, we're taking the derivative of u with respect to u. And then from here, to go from dv to v, we take the integral. So integral of e to the 2x dx. This is not so bad, but it's not exactly a basic integral, but we can the side here, so you have e to the t over 2 dt. That's more correct to write. You don't really have times dt, but then you can pull out this factor of 1/2, and you just have e to the t, because the integral of e to the t is e to the t. That's just one really nice property of this exponential. So you have e to the t, and then you have plus c, but we don't have to worry about that. We'll add that in to this integral later. But we have 1/2 e to the t is 2x, so you have to go back and plug that back in. So our integral here for v is going to be 1/2 e to the 2x, or just e to the 2x over t. That's the other part. So again, theoretically, you can kind of just do that in your head if you're comfortable with it, but if not, no worries. And then I'll just put a plus c there, but we'll just do that here, just because we're working with indefinite integrals. So just take this piece, this piece, this piece, and this piece, and we plug into this formula. So we have u, we have v, and we have v and du here. So the dv is just from the original formula. So let's just plug all of these in. So as you get quicker with these, you can just kind of do 2 times minus, but they're just little shortcuts you can do, but it's good to just kind of know the big picture idea of what we're doing here. So we have u v, so x times e to the 2x over 2. So I'm just gonna write that as that, and then minus v du. So minus the integral of v du, which is dx. So see how the fact that du is just dx makes this really nice. We just basically made this x part drop out of this integral. So this part we don't really care about, it's all done, and now we just need to simplify this. So I can pull out 1/2, and then I have this integral, which, funny enough, is what we just did here for dv, right? Yeah, so we can just plug this back into this integral. So sometimes it's not quite this nice, basically, because we have this exponential function here that it ends up repeating. There's a little bit of recursion here, but in general, we just have to treat this integral like it's its own thing to solve. So like we said, sometimes you can just do a simple u sub, sometimes it's another step for integration by parts, but it's just a different integral, but hopefully it's a simpler one than your original one. In this case, I can just do e to the 2x over 2, so I have examples here today, so let's just do sine x, but let's have an x squared. And now that I'm thinking about this, I think this might involve integration by parts twice because of this x squared. So, just like I said before, if I let u equal x squared, then when I take the derivative of that, I'll get 2x, which simplifies the integral, but it still leaves us with the factor of x. When I let this be dv, then we have this cycle with sine and cosine, but with positive and negative signs. So, as in like plus and minus, and then we have sine and cosine alternating because the integral of sine x is negative cosine x, right? Negative cosine x, and then you have negative sine x, and then you have cosine x, but you have those alternating. So this one looks like I will do something similar, but I'll do this part as u and this part as dv. We'll just see what we get here, I guess. But the integral of u, it's good to always start with your formula so you know what you're looking for. So here I'm going to let u equal x squared and dv equal sine x dx. I haven't worked this out, so I'm not sure if trying it the other way would work too. Although I'm thinking if you, okay, so let's say you let this be u and you let this be dv. When you integrate this, you're going to get x cubed over 3, but this part's going to kind of be stuck in this cycle, so I don't think that this integral is going to be any nicer than this. So I think this is probably the only way to pick u and dv for it to kind of, rather this is probably the simplest way to pick u and dv to make this work out. So from this choice, I will go ahead and calculate du. Just the derivative of this with the dx there, and v, which is just the integral of this. And in this case, that would be negative cosine x, and then you have a plus c, but we'll do that here again. So we have our 4 parts. This, 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 and this. So we have u, v, du. We only need u times v minus integral v du, so we don't really need this part, but we need it from the start to get v. So let's go ahead and plug this in. uv, so uv multiplying it, so positive, negative, so negative x squared cosine x minus the integral of v du, but because I have a negative here, I'm going to put plus, so v du, so 2x cosine x. Okay, so now basically this part's all done. We're going to look at this part. It looks like we're going to have to do integration by parts one more time, just because we went from x squared to an x. And so to get rid of this x one more time, we can let u equal this x. This 2 can come out front, so we'll just do this one more time. So basically we pick another set of u and dv's, no problem there, just, don't get them mixed up. U and v are just arbitrary variables here and placeholders for our pattern in our formula, so you can use other variables like f and g or s and t or whatever, but u and v are the more common ones, I think. So let u be x now, and dv be cosine x. So we're going to do this again. But just don't forget this 2 is multiplied by the whole thing. So then from here, we do the same thing from this choice. We get du is dx. From here we get v is the integral of cosine this first part is nice. Don't have to touch it, don't have to worry about it. But then hopefully this ends up being something that we can do. So we have negative x squared cosine x plus 2 times in parentheses uv, so x sine x. I'm gonna run out of room here. Minus v du, so minus the integral of sine x dx. Perfect. Which we know that the integral of sine x is negative cosine x, and then negative negative, so that should be plus cosine x. And then we still distribute this too, so let's just write it all out. X sine x plus cosine x. So hopefully this works out. And at this point I'm going to do the plus c. I should have done it here too, plus c. So I hope that this all works out, but this would be our answer. Negative x squared cosine x plus 2x sine x plus 2 cosine x plus c should be the integral of this thing. Should we check it, yes or no? Oh, okay. Let's do it. So, check. Let's take the derivative of this thing, okay? So lots of product rule practice here. So, take the derivative of one part, keep the other, then keep the first part, take the derivative of the other, add those, and then do this for each part. So the derivative of negative x squared is negative 2x. So I'm basically taking the derivative of this thing, okay? Just to check to make sure we get this. So derivative of that, keep this derivative of cosine x is negative sine x. So the negative and negative become positive. So x squared sine x. And then derivative of this is 2 sine x plus 2x cosine x. Oh boy, I really hope that this works out. And then the derivative of 2 cosine x is negative 2 sine x. Constant goes away. And let's see if stuff cancels out. So negative 2x cosine x cancels with this. And 2 sine x cancels with 2 sine x. So that's x squared sine x indeed. If that is not math ASMR to you, especially this part, I don't know if you experience math ASMR, honestly. When things just cancel out. You get x squared sine x, so that's perfect. So this is our integral here. In this case, we ended up having to use integration by parts twice. But again, once you get this first integral, just use whatever techniques you recognize. And if I do find an example where we use this multiple times, or if we use the algebra to solve the integral, if we use algebra to solve the integral, I will make a video on it, or maybe I can find a few examples and group them together, but this should probably cover the majority of the exercises that